Hi everybody, it's Nick. I wanted to give you guys an opportunity to have a little guided tour of the inside of the Quartex movements that I modify to add the crazy clock to it. This is how they come. This is just a standard Quartex Q80 12-hour movement. The 24-hour movements look no different on the outside. The only real variation is the length of the threaded portion of the shaft. They have different thicknesses for different clocks. My current stock is these here, which are designed for up to 1/4 inch of clock face thickness. And I have another one that's a little shorter that is 1/8. And the 24-hour movements, they only come in the quarter inch shaft length. These, by the way, these are ideal for retrofitting Zazzle clocks. If you buy a clock from Zazzle, it will come with exactly this movement in it. And you can buy a movement from me and simply swap out the black box for the one that I send you, and you're done. And that's an almost tool-free experience. Not quite tool-free, but almost. But anyway, what this video is to show you how I retrofit the movements as they come. I have boards that look like this. Just for comparison purposes, the standard Crazy Clock retrofit board it looks more like that, and you'll see that it's got 4 through-hole connections on it. The 2 up here under my index finger are for the clock, and the 2 over at far left are for the 1.5 volt battery. And then on the back is the programming interface. And these are good, but these require you to actually cut traces on the board that comes with the movement, and then solder wires in to patch it into place. And because I wanted to turn the volume up on this whole process, what I did instead is I went and designed this board, which you'll see momentarily why it's shaped that way. So first things first, we got to get inside. These weren't really designed to come apart, but it's not bad. You stick a screwdriver, that's a very narrow screwdriver, in here and pry this way, and that raises the tab above the catch, allowing it to slip past. It's a little bit fiddly sometimes, as you can see, but once you get it that far out, you flip it around and do the other one, because the case has to come off square or else it'll bind, and if it binds then it won't work at all. So now we can get the top cover off and set that aside. Now Quartex movements, the Quartex Q80 is particularly nice in that it has this plastic shell encapsulating almost all of the gears, which is very convenient. You want to lift that out and turn it over relatively quickly, because this plastic piece here, this plastic cover piece, is only a friction fit. It will come off, releasing this gear to fall out, and then it's kind of fiddly to put it back in place. Also, try and hold the base movement in this orientation, because these 2 little pieces of metal that form the battery contacts, they are also a friction fit, and they'll fall out as well. I actually generally put the knob on top of my little reel of solder, just because that way it sits flat. Now you can see the purpose behind having the retrofit board be the shape that it is. It has all of the same holes for the mechanical accoutrement that the original board has. There's just slightly more complex circuitry for the crazy clock, obviously. And then all of the cutouts, holes, and slots are for physical features of the board that we're replacing. So to get the old one out, it's 1 screw, which we need to save because we're going to hold the other one, the replacement, back in. And then you have to desolder the coil. It's these two contacts down here need to be desoldered and removed. You have to be a little bit delicate about this operation because the coil wires are simply wrapped around the post and soldered in place. So those connections won't stand up to too much abuse. So you have to be a little bit delicate. Fortunately, they did use lead-free solder, which really doesn't want to stick to anything. So the solder sucker, usually with one pass, will free up the pins quite nicely. You also want to make sure that as you're doing this that you approach from the correct angles, because you don't want to use the soldering iron to melt any of the plastic pins that are part of the gear train assembly, because then that'll make pulling the board off just that much more difficult. You also sometimes need to fiddle a little bit with the pins after you've removed most of the solder, just to make sure that what's left behind doesn't try and stay. Having done that, now we've freed up the old board. I've got a pile of these by now. I jokingly tweeted to Clockit to ask if they wanted them back. I don't really know what to do with them. I guess if you have a use for very, very accurate 1 pulse per second 1.5 volt driven oscillators, there you are. You can also rescue the crystal off the back. It's a nice through-hole part. Okay, well, we'll set it aside for now. So the next thing we got to do is put the new board in place. I'm not quite ready to do that because this one needs to be calibrated, which I'll make the subject of a different video. But I'm going to pause right here and I'll come back when I'm ready to put this board in place, and we'll pick up where I left off. Okay, we're back. This movement has this controller has been calibrated now. In this case, the guy asked me to calibrate his movement, and it came out to a drift of 2.4 parts per million fast. The way I measure that is I load special firmware in that just outputs a square wave directly from the crystal, and then I measure that over the course of 10 minutes against a GPS receiver, and the answer comes out that it was 2.4 parts per million fast. So that factor has been programmed into the firmware. Now, the individual crystals have a tolerance of 10 parts per million, but across a manufacturing batch, there can be other imperfections and other tolerance variations in the parts, so that what winds up happening is you have to calibrate at least a batch of manufactured boards so that you come up with kind of an average factor from which you can deduce that the members of that batch will only vary by up to 10 parts per million. But you don't know if it's 10 parts per million from plus or minus maybe 20 parts per million, so anywhere from 10 to 30 parts per million. So you program in a batch compensation for a manufacturing run. But in this case, the guy asked for his particular movement to be calibrated, so we actually ran it for this particular board and then programmed in that compensation factor into the EEPROM. But now, it's time to actually put the firmware in that he asked for. He asked for the lazy clock, so I have here a pogo pin adapter that's hooked up to my Raspberry Pi, which you can't see off camera, and that's going to do the AVR dude thing for me. So we make contact with the programming pads on the board, and then upload the code. Because the crystal is also the execution clock for the controller, it's running at 32 kilohertz, so the programming operation has to proceed relatively slowly with an SPI clock of about 4 kilohertz. So it takes it a good 20 seconds to load the code in, and then another 20 seconds to verify it to make sure nothing bad happened on the way in. So that'll just take another 15 seconds or so. Just about there. Almost. And we're done. Okay. So now the board has been calibrated. It's had its code loaded. Now we can actually put it on the board. It's best to make sure that the initial programming steps, all the stuff you're going to do with the AVR programmer, are done before you get to this point, because two of the programming pins are also wind up going to the coil, and the coil is a relatively low impedance load, so that can interfere with programming operations if your programmer isn't tolerant of loading. If you have to reprogram in the field, I've made a provision for that. This little solder jumper down here in the corner has a trace running through it. If you cut that trace with an X-Acto knife, then it will disconnect the coil, or at least one of the coil wires, and having one of them disconnected means that the other one is a moot point. So you run an X-Acto knife between those two pads to break that trace, then you should be able to program with no problem, and then before you reassemble the movement, you just short those two pads back together again with a little ball of solder. But in this case, I didn't have the coil hooked up at all, so it wasn't a problem. But even so, my programmer doesn't have any trouble with this loading on it in general. Okay, so you put the board on there, and I like to screw it down first rather than soldering it first, just to make sure that if the board needs to move around under the influence of the screw, that it has the freedom to do so. It's really easy to strip the screw head, the screw threads in that soft plastic a little bit, so you just get a sort of almost like the equivalent of finger tight with a screwdriver, and then you're good to go. And then lastly, we solder the pins down. Again, you want to try and use as light a touch with this as you can, because you don't want to abuse the pins and the coil wires that are wrapped around there, if you can get away with it. Now that the board's in place, we just put it back in here, we flip it upside down and quickly stick it in the hole, making sure that you don't let that square gasket thing fall out on your way. Once it's gone this far, it's sometimes helpful to get yourself a AA battery and stick it in there before you put the case on. If you hold it up to your ear, you'll hear it tick. In this case, I don't. Sometimes you have to push down a little bit. The case will actually mash the contacts in to the battery contacts, and if that doesn't make a good contact, then it won't work. Yeah, and now it's working. So now all that's left to do is to put take the battery out and then put the lid back on. Make sure you put the lid in. The lid only really fits one way. You stick it down so that the snaps pass through, 2 clicks, and we're back together again. That's it. So this one's ready to ship out. Thanks for watching.